Hey everyone, I'm very excited to be here. My name is Stav, but you can call me Stwo. And I swear I thought it's a cute nickname even before I found out it's the name of the fastest prover in the world. Wait, I hope you've heard of Stwo. If not, the next slide, I need this one, is for you. So Stwo is starkware, our next generation prover. It is based on Circle Stark. This is a beautiful math that enables efficient Stark over a Mersenne prime fill, specifically with p equals 2 to the 31 minus 1. This prime allows for fast arithmetic, and it makes Stwo incredibly high-performing. High-performing. Okay. If you're out of the zero-knowledge proof system, zero-knowledge world, let me give you some context. So in the zero-knowledge proof system, the prover job is to convince the verifier that some sort of statement is true, without revealing it why it is true. And the verifier needs to check it with minimal effort. So in our setting, the prover is Stwo, and it is responsible to generate a proof. To do that, it uses some sort of description of the calculation called AIR, Algebraic Intermediate Representation. But I will explain more on it on the upcoming slides. Anyway, back to me. So I'm part of the engineering group at starkware. Specifically, I'm on the AIR design team. We are responsible to find clever ways to translate any statement you want to prove into its AIR representation. Don't worry. If you want to use Stwo for proving, you don't need to write this translation yourself. We've already done that for you. We implemented all the necessary AIRs for Cairo. Cairo is a general-purpose language, very similar to Rust, that lets you code anything you want to prove. But if you join me today, I guess it means that you, just like me, are a bit curious to get a sense of what's going on under the hood before using it as a black box. So let me show you how you can take a complex function like the Blake-Ash function and turn it into a set of polynomials. Let's start from the beginning. What exactly is AIR? So as I said earlier, AIR stands for Algebraic Intermediate Representation. And it basically contains all the information the prover and the verifier need on the computation in order to generate or verify a proof. It contains two things. The first one is the execution trace. This is a table of field elements that represent the calculation steps. And the second thing is a set of polynomial constraints on the columns, which must be satisfied by every row in the trace. Let's just have a concrete example. So we'll take a look about this function, the split function. It is very simple. Given a 16-bit number x, we want to split it into its low 8-bit and high 8 bits. So let's start with writing together the trace. And now I'm going to give you a rule of thumb. Every trace starts with the component's inputs. So if the input is x, what will be the first trace cell? Yeah, that's true, x. And now the next trace cells will be the calculation, and it is very straightforward, so I think you can do this as well. What will be the next calculation step? Very straightforward. We want the lower 8-bit of x and the higher 8-bit of x. Okay, this is an option. I put just something more simple, but yeah. X shifted right by 8 and x shifted left by 8. Yes, but not cyclic rotation, just shifting. But it gives you the higher bits or the lower bits. Anyway, I just want to mention that this is only the recipe. In the trace, the prover writes down the actual values. So if I needed to calculate the split function on the value 1, I will write in the trace, not me, but the Stwo, the prover, 1, or me, and Stwo, 0, and then 1. And if later I was needed to calculate the split function on the value 5, I would write 5 and then 0 for the higher part and 5 again for the lower part. So the second dimension of the table, meaning the rows, are actually different instances on the same computation. Now let's move for the constraints. So let's look about this. We are taking the call 2, which is the lower 8 bits of x, and we are summing it with call 1, which is the higher 8 bits of x, multiplied by 2 to the power of 8. As you know, multiplication by 2 to the something. Really? Okay. It's just like shifting it to the right by 8. So we actually put those 8 bits and put it in the correct value. And then we said it equals to x, called 0. You probably now just be thinking, wait, what? We just took x, split it into 2 parts, put it together, and said it equals x. Of course, this constraint is old, like it's trivial. So here's the key point, and this is an important one. The verifier never actually sees the trace. The only thing he sees is a polynomial that the prover constructs for him from the trace. So if the prover fills the trace with incorrect value, it will result with a set of polynomials that misbehave. And the verifier will know to reject the proof. I don't want to get into all the Star protocol magic right now, but if you're curious, I highly recommend you to read the paper. It explains all the details beautifully. Anyway, back to what we are really here for, figuring out how the error for the Blake hash function looks like. So I will start with a quick overview. So the Blake hash function is a cryptographic hash function, very known for being secure, fast, and surprisingly kind of simple. Let's take a look. So we have as an input 2 vectors, one of a state called v, one of a message called m. Each one of those vectors contain 16 words, where each word is 32 bits. For them, we're applying the run function, and it results in an update state. We take this update state along with some fixed permutation of the message. And when I'm saying fixed, I mean that the indices are known ahead according to the round number. So for example, for round 2, it's going to be M15, then M11, and so on and so on. Again, we are applying the run function, and again, resulting in an updated state. We goes on and on like this for n rounds, where n is determined by the specific variant of the Blake being used. And the final step is the Blake hash function output. What's going on in every round? So the round function is just called the g function 8 times. Every time on a different subset of word from the input. So for example, in the first call, it's going to be on v1, v5, v9. You can read it. It's not interesting. Where most of the logic happen, it's the g function. G takes as an input 6 words and modifies in place the first 4. Using 2 functions, that's it. Triple sum and bitwise XOR rotation. Today I chose to focus on the bitwise XOR rotation because it demonstrates some cool thing I want to show you. But after this talk, I hope you have all the tools to build the full Blake hash function yourself. Yeah, so be patient. We'll get there. You probably noticed that most of Blake is function calls. I mean, it applies the same logic over and over again on a different shuffled version of the input. Now, imagine a world where you need to write this function without using function calls. Pretty messy, right? This is why Stone Air Designer looks like that. And for those who don't know, Stone is our previous prover, and it stands for Stark 1, where Stwo is Stark 2. But thanks God, those days are over, thanks to Stwo and its flat air design. This is us right now. Pretty cute, right? So flat air design in one sentence means that every component, every function is proved in a different table, and those tables communicate via lookups. Let's have an example. So remember G from earlier? That one? Let's start writing its trace together. So the input is, fuck, I just gave you the answer, but what will be the first traces? The input. So we have 6 words as an input. We're writing down to the trace. And now the first thing we want to do is we want a triple sum of A, B, and X into A. Now, let's assume that we have a different component called triple sum that enforces that the last column is indeed the triple sum of the first 3 columns. I put here some question mark because I don't want to dive into the full R implementation. It's not that trivial, but let's just say we have this component and we know that the constraints actually enforces this claim. So what I will do, I will write down A to the caller G trace and add something called a lookup constraint into this triple sum component. Lookup constraints means that the tuple A, B, X, A tag appear in some row in the triple sum component as an input and output. Of course, this constraint encoded into polynomials, but I keep the math behind it for another lecture. I just want you to get the principle. We're good. Okay, I want to show you another cool usage of the lookup. And this is a lookup into a constant component. A constant component is a component whose trace doesn't depend on any input. It's just fixed. It is known ahead. The verifier doesn't need any constraint. It can just calculate it or look at it or whatever. So imagine we have a table where the first 2 columns are all the possible pairs of 8-bit numbers. And the third column is their bitwise XOR. Now, let's say I'm in another component and I want to enforce bitwise XOR calculation. I will just add a lookup constraint into this table. Okay, we're almost ready to implement the first error. We have all the tools to do it. I just want to start with a quick definition of the function. So the bitwise XOR rotate by 8, I just chose it, means that given 2 numbers, each one 32 bits, we want to return their bitwise XOR rotated to the right by 8. And this time, this is a cyclic rotation. So for example, if we have those numbers, we're going to XOR bit by bit with the corresponding bit. So 0 XOR F is F, 0 XOR 0 is 0, and so on and so on. Then we will take the lower 8 bits and put it in the higher 8-bit position. And this is the output. Yes, we're ready. Exciting? Yeah. Okay. What will be the first thing in the trace? The input, yeah. But now that you are grown up, I need to tell you something I've been hiding for you. And this is the fact that you can't actually write a 32 bits words into one tracer, because our field element max is in 2 to the 31 minus 1. So we will need 2 tracers in order to represent a 32-bit number. And the way we are doing it is taking the lower 16 bits and the higher 16 bits. So for 2 32 bits word input, we will have AI and A low for A, and for B, BI and B low. Now let's use the GAN from the first scene. Remember the split function? Given a 16-bit number, we want to split it into 8-bit chunks. So, and we are doing it in order for the bitwise and for the rotation in the end, you will see. So we split AI into AI and AI low, and we split A low into A low I and A low low, and so on and so on. Then we are writing the output to the caller trace and add a lookup constraint, which is now an arrow, so use your imagination. And the next thing we want to do is the bitwise XOR. So we want to XOR the corresponding bits. So we want to XOR AII with BIII to get CII, and so on and so on. And I just want to remind you that this is a constant table. So these rows appear somewhere in the table because the first two columns are all the possible 8-bit numbers pair. So again, we are writing the output into the caller trace and add a lookup constraint into the table. Now the last thing we need to do is the rotation. For this, we don't have a specific component, so we're just going to do it in line. So we'll start by writing the output, which is also a 32-bit, so also 2 traces. And now let's think together what will be the constraint on those traces. So if we take a look on the bitwise XOR output, we have CII, C high low, C low I, C low low, and we want to take C low low, which is the lower 8 bits, and place it into the higher 8 bits position and shift it all the others by 8 to the right. And now you can see that D high contains in its higher 8 bits C low low, and in its lower 8-bit position, CII. We know a constraint for that. We know. This is just as before. So DI equals C low low multiplied by 2 to the power of 8, with shifting the 8-bit value into the higher part position and summing the low part. And we're doing the same for D low that contains C low I as is lower 8 bits and C high low as is higher 8 bits. Good job, you did it. You implemented the first error yourself, and now your mother can finally be proud of you. But don't get too excited, because writing errors is fun, but writing an efficient error, this is where the challenge begins. And when I say efficient, I mean that we need to minimize the number of traces for the prover, and we want to minimize the number of columns for the verifier. So good luck finding a suitable balance. And now, I want to show you that we at starkware know what we are doing. Let's just let the number talk. For those who only came for the benchmark, please wake up. This is your moment. So we chose to focus our optimization efforts on the Blake chain. Blake chain means that we apply the Blake function over and over again for n times. This is a key component in the Stark protocol, specifically when you're hashing Merkle trees. So that's why we chose to focus on that. And as you can see, for n that is greater than 512, Stwo outperform the others. And this is the range we care about. Yeah, so thank you so much for joining my super technical talk. I'm attaching here some useful link if you want to further explore. If someone wants to try to build the full Blake hash function, do it. You can, don't hesitate to come with any question. Thank you. I was Stwo.
If you have any questions, just raise your hand. I'll bring the mic to you.
Thank you. Nice talk. I have two questions. The first one is, why do you care about Blake 2 in particular? It's not, as far as I know, a hash function that is used a lot in blockchain. So, okay, maybe it is, just wondering. The second question is, why do you need to split the 32-bit word into a 16-bit? Yes, sure, you will be missing 1 bit because of the modular arithmetic, but your constraint will still hold. So why is it so important to do the splitting?
Okay, so for the first question, so Blake is used in the protocols. Specifically, we recently changed to use the Blake because it's known for being very fast. So we changed, I think we used Poseidon earlier. And now we use Blake, and it's improved the performance significantly. So this for the first question. But you're right, in the past we didn't have error for it. We just knew for Stwo. And for the second question, because think about that the function definition is given a 32-bit number. So if you're gonna get a 32-bit number and the error don't know how to handle it and the constraint won't hold, we can look into the math later, you need to calculate for the given input, and the input doesn't know which field element are we using or something like that. So we just need to be able to calculate for any kind of input. So this is why. I answered? He's worried that I didn't answer all of your questions. Ah. Another questions?
Thank you, man.
Thank you, ma'am. Thank you.